so the learning targets, the overall reaching on a course is exchanges of energy when you have reactions and creating solutions. But in this particular one, we're looking at writing out the reaction that corresponds to enthalpy changes for formation, combustion, solution, vaporization, fusion, and neutralization. Also use bond energies to calculate delta H with this formula, okay? And use the dot structures to be able to figure out from the bond energies, okay? We'll be doing that. This is like the first half of the notes. Then we'll be looking at colorimetry for the second half of the notes, okay? So keep that in mind. All right, just a quick review of, going back over that we're looking at things from the system perspective. Everything that's not the chemical is part of the surroundings. Heat, of course, is going to transfer from the system to the surroundings, okay? So endothermic versus exothermic. Heat flow into the system, absorbing energy from the surroundings. Going back over these terms, we're going to use them all the time now. Exothermic, energy flows out of the system. Energy is gained by the surroundings. Core must be equal to the loss from the system. Okay, this is an equal magnitude type of thing. So that's the first law of thermodynamics, law of conservation of energy there. Going back over that. All right, going back over what enthalpy means. So change in the energy of the products and the reactants here. It's a state function. So we go for the initial and the final. We don't really care about the pathway here. We will start looking at pathway stuff though when we get to kinetics. So it's not that we don't care about the pathway, it's just under a different overreaching unit topic. Delta H, of course, is equal to the heat at constant pressure. Remember, we factor out the work aspect because the work change is very minimal. So we really are only concentrating on the heat that's going on during in the reaction. Okay, so enthalpy here, review, state function. The generalized equations right here, the products minus the reactants. Okay. There is a more formal equation on your formula sheet. We're going to get to it, the formation equation. And we will be calculating using that. All right, delta H of reaction describes the energy changes for a reaction. Kind of showed you that a little bit. So when delta H is negative, it means it's exothermic. Delta H is positive, it means it's endothermic. Okay? The sign denotes the way the energy is flowing, the heat is flowing. So negative sign means it's being released. Positive sign means it's being absorbed into the system. Okay? So we are going to be looking at a bunch of different delta H's that have different little subscript next to them, like reaction. Some are generalized reactions. Some of them, though, are combustion reactions, so they put the delta H of combustion. If you're making a solution, they put SOL next to it. So you're going to see these delta H's with little different subscripts next to them referring to the reaction or the solution that it's being made. Okay? Now, you probably remember these from last year. These are potential energy diagrams. Okay? And you do need to know how to read them and know like which one's exothermic, which one's endothermic. Because sometimes they give you the reaction and the delta H right next to it. Sometimes, though, they provide you one of the potential energy diagrams, and that's supposed to tell you, based off of your analyzing of it, whether you're dealing with an exo or endothermic, so you know how to put the sign on the delta H. Remember, for exothermic, these guys, exothermic, your reactant energy up here is going to be higher than your product energy over here. Okay? So it's products minus reactants. That means the delta H here then ends up being negative because the products will subtract the reactants and you'll get a negative sign on it. The activation energy is the amount needed to get it started. That's more of a kinetics thing, so we will talk more about activation energy later, that getting to the top of the hill, and the catalyst part and all that stuff. That's going to fall under kinetics, but for right now, you have to recognize whether it's endo or exo based off of the diagram. You're really looking at the reactant and the product amount of energies and being able to subtract those, okay? In the endothermic reaction, it's pretty much the same thing, except for your reactant energy is lower, then your product energy, which is higher. So this difference here ends up being a positive delta H, okay? That also means energy is being absorbed into the product bonds, okay? So if you're looking at the endothermic, the reactant energy, the amount in those bonds is less than at the end, the new products, their bonds have a higher amount of energy stored in them. That's why it's called potential energy, because it's a storing in the chemical bonds here. Going back to the exo one, just remember that the energy of the reactants in their bonds is higher than the bonds that are the energy that's stored in the product bonds. That's why some of that extra energy has to go somewhere, and it leaves and goes to the surroundings. Okay. So keep in mind, we're looking at that. So make sure that you can tell between the two, looking at the reactant product line, as to whether you're dealing with endo or exo. Like I said, sometimes they give you the delta H, sometimes they give you the diagram. Okay, sometimes they tell you that it's being released or absorbed, so you have to know the direction that way. Okay. So, formation. Now we're going to look at delta H of formation. And it is what it says, it's the forming of a compound from its elements. The key here, though, is you're forming 1 mole of the substance. Only 1 mole. And this is why you probably noticed in the Hess's law problems that there's those fractional coefficients. Well, this is because when you're trying to come up with the heat of formation, you're basing it off of 1 mole of the compound. And so then some of the reactants end up becoming fractional. Okay? So, enthalpy change for formation for 1 mole of a substance. And it's going to form from its elements. Okay? For example, what would the reaction look like that describes the formation of water? So, obviously, our product is going to be what? It's going to be water, right? What 2 elements are going to form water? Hydrogen and oxygen, but both are diatomic, so you would have to write them out like this, yes, okay, H2 and O2. But it's here is where the tricky part about the balancing comes in. This has to remain 1, okay? So if I'm balancing the H's, which is fine, the H's are just going to be a what? 1 as well, okay? And for the ones, you really don't have to put them in because it's understood 1. But for the O2 is now affected. We cannot multiply through. We have to just go with 1 mole of water. So that's going to end up being what? This is going to end up being a half here. And that's where we get our fractional coefficients. Okay? So I'm going to have you go ahead and try. Yeah, there's our answer. H2 plus 1/2 O2 is going to give us 1 mole of water. Okay? 1 mole of the formation of the compound. That's why it's called formation, being formed from its elements. Now, I want you to go ahead and try forming methanol from its elements. Okay? So you have more than just hydrogen and oxygen in there, and another element up there. And you want to form methanol from all 3. So go ahead and try to do it real quick. And balance it as well. Okay, so let's take a look here. All right, forming methanol. 1 mole of methanol means you need carbon. What does carbon exist as at like normal conditions? Solid. If you look at the periodic table over there, all the ones that have their symbols written in black are solids at normal conditions. The green ones are going to be gases, and then the blue ones should be liquids at, but they say 30 degrees, which is a little bit above standard conditions, but for the most part, that gives you a good idea of like normal phases, okay? So if we wanted to put the phases in, then we would do that. Of course, oxygen's a gas, hydrogen's a gas. Methanol, all the alcohols are really liquids at our normal conditions, okay? Yes? Well, we're forming it from its elements. So what are the elements in methanol? Carbon, hydrogen, and oxygen. So formation is always going to break down to its elements, forming the compound. Okay? Combustion, though, means you're taking an organic compound, a hydrocarbon of some sort, combusting it, and producing what? What do we always produce out of combustion reaction? Carbon dioxide and water. What is always the other reactant in combustion? Oxygen. So, same deal here. You're going to undergo combustion, but it's going to only be 1 mole of that hydrocarbon that gets combusted. So everything gets balanced off of that 1 mole of the hydrocarbon. So when we're talking about, delta H of combustion, delta H of formation, it's always based off of 1 mole of that substance. So everything else gets balanced, and that's why we see those fractional coefficients. Okay? So 1 mole of the organic compound is being combusted. We're looking at an example here. If we were combusting methanol with oxygen, we would get carbon dioxide and water, but we're balancing it off of this guy. This guy gets the 1. Everything else has to work around that guy getting the 1, the organic compound getting the 1. So the oxygen ends up being 3 halves. The carbon dioxide is also a 1, but the water is balanced with a coefficient of 2. So that's one particular example of that. Now you're going to try the next exercise, see if you can set it up for benzene and balance that real quick. Know how to balance combustion to make it efficient. What do you always start with first? C, then you do H, lastly O. But balance the O's last because O isn't the other reactant by itself, so it's much easier to balance at the end. You always start with C, then balance your H, then look to balancing O last. We call it the choke. Okay? CHO. Follow that order, it'll be a lot easier to balance. Alright, did you get the 15 halves of the oxygen? The C here, so, like I said, balance the C first, then the H, then you add these up. So this is 12 oxygens plus the 3 oxygens gives me 15 oxygens. But since I have a 2 here, I just divide it by 2 and then I can put in my 15 halves there. That goes in here for the oxygen. Does that make sense? So balance C first, balance H, then add up your oxygens, divide that by 2, and you can stick it over there. Does that sound good? Not too bad. Okay. Molar heat of solution. I imagine you probably understand we're still working off the idea of the 1 mole. 1 mole of the compound, we're we're dissolving it in water to form the solution. Molar heat of solution shows 1 mole of the compound dissolving in water. So this is like taking sodium chloride, any salt, any soluble salt, and putting it in water. 1 mole of it, though, how is it going to break down when it dissolves? And remember, when we're dissolving, you have to overcome the hydrogen bonding of the water. You have to overcome the Coulombic attraction of the ionic bond so that it can form that ion dipole bond. And that actually requires an energy change. And it does happen to have one. Even though it's a physical process, there is some energy change going on when you have the hydrogen bonding and then you have the Coulombic attraction reestablishing that ion dipole force. Okay? So, looking real quick at one example, okay? It's going to be the heat released or absorbed by adding it to the water. Some things will heat up, some things will cool down. We're going to do a hand warmer lab and investigate some of these salts and how much they're going to heat up a solution. Look at that, okay?